Hello. So this is a lesson for the second part from Chapter 3. And if you're watching this before we've had a chance to explore these in class, a little prior warning. This is a lesson that, upon first glance, a lot of students seem to, it looks to them like this is really complex, and it looks a little bit daunting in terms of some of the algebraic work. But it ends up being one of the lessons of the course that students actually do the best with. Because there is a process with a bit of practice. It's pretty doable. It does look kind of crazy, so don't let your initial fearful thoughts kind of cloud things. Like I said, most students actually in this course find this one of the easier parts of the entire course with a bit of practice. I have to keep saying that, with a bit of practice. So before I talk about this remainder theorem here, which I'll get to in a bit, let me talk about long division. Now if we divide something using long division, let's say I want to do 312 divided by, 9. Let's recall how we do that. We put 312 here, 9 is the divisor, we put it here. We then first think about how many times does 9 go into 31? Well, 9 doesn't go into 31 an exact number of times, but at the closest we can get there is if it goes in 3 times. And then we go 3 times 9 is 27. We put 27 right here, lining everything up very carefully. And then we subtract just these from each other. 27 subtracted from 31 is 4. And so we then bring down the 2, and we think about how many times does 9 go into 42. What we've really done, by the way, this 3 here actually stands for 30. It's in the 10 spot. What we've really done is we figured out how many times 9 goes into 310. That's what we really did. And 9 goes into 310 30 times. Okay, but we don't have to think about those when we just perform the sort of algorithm here. And so now we bring down the 2, and now I think, okay, how many times does 9 go into 42? 42 is not a multiple of 9, but the closest number to that is going to be 4. 4 times 9 is 36. We then go back and repeat the algorithm. We multiply the 36 down here. We subtract again. I'm repeating the same steps. And we get 6. And now at this point, sometimes we can decimalize it and we bring down a 0. Or when you first learned about this, we'd actually call that the remainder. And we'd say that, if this was grade 4, we'd say that 312 divided by 9 equals 34 with a remainder of 6. That remainder of 6 means there's that many left over that can't be formed into a perfect group. Okay, so I want to do the same thing now, but with polynomials, which sounds more frightening, but really, it's the same sort of idea. And so what I want to do first is set up my long division here, that my polynomial that I'm dividing by, or dividing into, whatever you want to call it, goes right here. So I'm going to write 2x cubed minus 2x squared plus 1. You may have noticed I left a bit of space between 2x squared and plus 1. I'll get to that in a bit. And x minus 3, that's the divisor. That goes right here. OK, now that little space I left right here, that's because my polynomial, my numerator, doesn't have any x terms in it. But I want to create a spot for it, which is pretty easy to do. Just, put 0x. There we go. Now I got a spot for it. Haven't changed the meaning of the expression of a polynomial, but I've created a spot for it. So now what I want to do is start my division. And I could start by thinking about how many times does x minus 3 go into that? Well, I don't know. It's a bit too much to think about. So what's easier to think about is just pay attention to the first term in each pair. How many times does x go into 2x cubed? X times what equals 2x cubed? Maybe already you kind of know what that is. X times what equals 2x cubed? Or another way of thinking about it is the other way around. 2x cubed divided by x equals what? The two questions I just asked are the same thing. They mean the same thing. And so maybe one of them looks easier to you. In the end, they both equal 2x squared. And so that's part of my quotient. That's what goes above the symbol. But I have to line everything up, so I put the 2x squared above my x squareds. OK, that's my first step done. Then I multiply. I multiply this by the whole divisor. There's 2 terms. So 2x squared times x is 2x cubed. And 2x squared times negative 3 is negative 6x squared. So what's next in our algorithm? Next we subtract. We subtract all of this from what's above it. All of this here. Now, got to be a little bit careful. The first part, 2x cubed minus 2x cubed is 0. That's easy. we got to be careful right here. Minus 2x squared minus a negative. There's a lot of negatives going on. So what I'd actually recommend doing is going back a moment. And instead of writing it like I did here, realize that everything I have inside these brackets, when I subtract, is going to be changing sign. So I'm going to rewrite this as negative 2x cubed plus 6x squared. It's the same idea. So I'm going to write it like this. When I subtract all of this, this becomes negative, this becomes plus. And now I can just combine like terms. That cancels out. And I personally find this easier, and most students seem to find this easier, to just now think, okay, what's negative 2x squared plus 6x squared? Well, negative 2 plus 6 is 4, so 4x squared. And then we bring down the next term, so plus 0x. And then I repeat the algorithm, now paying attention down here. So I now got to think x times what equals 4x squared? Or 4x squared divided by x equals what? It's the same thing. I'll go with, x times what equals 4x squared? X times 4x equals 4x squared. So I put that above my x column. Go back and multiply. 4x times x is 4x squared. 4x times negative 3 is negative 12x. And now I subtract these. Again, I'm subtracting all of this from the terms above. I'm going to just rewrite it like this. I'm going to write as minus 4x squared plus 12x. And now combine like terms. That cancels out. And have just 12x right here. And then bring down this 1 for my last step. And now I need to think about how many times does x go into 12x? Notice each step keeps getting easier and easier. That's how long division worked as well. Your numbers keep getting simpler as it goes on. So x goes into 12x 12 times, 12 whole times. Put that up here, positive 12. Go back and multiply. 12 times x is 12x. 12 times negative 3 is negative 36. But I'm subtracting both these from what's above. So when I subtract them, this becomes a negative, this becomes a plus. That cancels out. And I have 1 plus 36, which is 37. And that's my remainder. So what does this all mean? Well, this means that if I go back to my original statement, if I go back to this, 2x cubed minus 2x squared plus 1 divided by x minus 3 is the same as my quotient, 2x squared plus 4x plus 12. But there was a remainder. So I have this little remainder here of positive 37. And so what does that mean? That means there's a bit more I got to put right here. And so 2x cubed minus 2x squared plus 1 divided by x minus 3 equals what I have highlighted in green, plus, not 37, plus 37 over my divisor, x minus 3. Now, if my remainder was 0, if I had no remainder, then this term here wouldn't exist, and my answer would be a nice clean division. There would be just a quotient. But there was a remainder, and so my remainder, again, doesn't mean plus 37 extra. It's 37 over whatever I'm dividing by. And this here and this here are equivalent. Lastly, let me now come back to the remainder theorem. The remainder theorem says here, if you have any polynomial, in this case, the polynomial I'm dividing by is what I've been highlighting in yellow. If you divide it by a binomial of the form x plus a, in this case, I was dividing by x minus 3. The remainder is always equal to f at negative a. What that's saying is that the remainder of 37 here, I can figure out, alternatively, I can figure out by just looking at what I've highlighted in yellow, 2x cubed minus 2x squared plus 1, and replacing x with positive 3. Because again, I have a minus a there, I have a plus a right there. So if I look at my divisor of x minus 3, I'm going to, if I'm dividing by x minus 3, if I put positive 3 into these x's, I know I'm going to get out 37. Okay, so let me just show you in my calculator. I'm going to go to my calculator in a moment, and instead of 2x squared plus 4x plus 12, instead of 2x cubed minus 2x squared plus 1, the polynomial I was starting with, my numerator essentially, if I replace all those x's with 3, I know I'm going to get out 37, the remainder. So first let me show you that's true. And so let me type in 2 times positive 3 squared. minus 2 times positive 3. Oh, sorry, this should be cubed. There you go. Minus 2 times positive 3 squared plus 1. So I'm just going back to the original polynomial and that I was dividing with the numerator, replacing all the x's with positive 3. And notice you can see right here off the side on my screen, it says equals 37. Now, why is that important? That really, right now, it's not that important. It'll come into play for the next lesson. But notice I got the same remainder I got here. Now, remember what I said at the very start of this lesson. This is one of those lessons that if you look at the video before you actually try it in class, it seems kind of daunting. So if that's you, if you're looking at this before you've tried it in class, I'm glad you're looking at the video in advance. But you're probably maybe feeling a bit overwhelmed by all that I've done. Fair enough. Things should get more sensible, perhaps I'll say, once we're in class. But I just hope you trust me. I've taught this course many times before. This is never a part of the course that holds people back as long as you have a chance to practice things. And yeah, right now this got a bit messy. I'm explaining things. We only have one example. It is a bit time consuming. But once you go through the process, it's not hard. It takes up a bit of space, but it's not hard. Okay? So that's it. There is a way of speeding this up. And that's called synthetic division. And that's what I want to talk about here. And again, if you haven't seen this already in class, this is going to go by quite quickly. For synthetic division, it's a shortcut and a real shortcut for dividing polynomials like this. It's really good for dividing when your denominator, your divisor, is just like x plus or minus some number. If there's like a 2 in the front of here, then what I'm about to do doesn't really work so well, and you're better off just doing long division. Okay? If there's like a 2 right here, then there'd be a 2 right here, and you go through the same sort of steps. It wouldn't be any harder, really. But with synthetic division, what I'm about to show you, if there's any coefficient in front of the x instead of 1, then what I'm about to do is possible, but you have to change some of the steps. I'm not even going to teach it to you because at that point, you're better off just using long division. All right, so how does synthetic division work? Well, first of all, this is my polynomial that I'm dividing by. This is my divisor. Okay. First, before I even go on, let me see what the remainder is going to be. Okay.
Ms. Graywell, call press on 801. Ms. Graywell, call press on 801.
So using the remainder theorem, is the title of the notes, if I'm dividing by x plus 2, I know if I replace all these x's with negative 2, I know whatever number I type into my calculator, or I could do it by hand, but I'm going to use a calculator, should be my remainder. Okay, so I'm going to take this, x to the power 4 minus 2x cubed plus x minus 1. I'm going to replace all those x's with negative 2. And whatever number comes on my calculator, I know should be my remainder. Okay, so let me just do that really quickly right here. So I'm going to type in bracket negative 2 to the power of 4 minus 2 times negative 2 to the power of 3 plus negative 2. Take away 1. Okay, so you can see it says equals 29. So right now, that 29 doesn't mean much to me. I'm just pointing out how when we do some work in a moment, that 29 will be also the remainder of my work here. Okay, so that there, I know before I've done any work, I know that this is going to have a remainder of 29. I kind of make a little note here. I knew that by using the remainder theorem, which is the very first part of the lesson. Remainder of. Okay. But again, why that remainder really can be of use to us really will come into play for the next lesson. All right, so that's why we've got to be a little bit patient. But so, how do we do synthetic division? Well, for synthetic division, the first thing I want to do is set up this sort of L-shaped thing with it. I have 2 lines that I want to write with. In the top row, I just want to write down the coefficients of my polynomial. My coefficient of x to the power 4 is 1. The coefficient of the x cubed is negative 2. There is no x squared term, so I will need to put in a 0 right here. The coefficient of my x term is 1, and the coefficient of my constant term, or the constant, is negative 1. So the first thing I've done is just wrote down just the coefficients. Again, creating a spot like I did in the last question if I'm missing a particular term. All right, next, whatever I'm dividing by, x plus 2, right here, I'm going to put not the x. All I really care about is the plus 2. And if I have a plus 2 there, I'm going to put a minus 2 here. I'm going to always put the opposite number. Now, there are different ways of showing this. I'm just showing you how I approach this. And so if you've learned this before, it's not wrong to put a plus here, but then your steps coming up will be a little bit different. OK? So I want to just show how I generally approach it, although I will make another comment about that later. That's it. Now I'm set up. So what do I do? How do I divide this? Essentially, I'm just focusing on coefficients. First, we always just bring down the first number, 1. Then what I do is I take that 1 and I multiply by whatever number is here. So negative 2. 1 times negative 2 is negative 2. And I put that right here. Then what I do is I just combine these two together. Negative 2 and negative 2 is negative 4. And then I'll make that negative 4 a bit neater. Oh, that makes it even more messy. Let's try that again. All right. Then I take that, and again, I multiply by negative 2. Negative 4 times negative 2 is negative 8. I put that right here. Then I combine these together. 0 plus negative 8 is negative 8. And then, perhaps you can guess, I multiply that by negative 2, which is positive 16. Oh, wait a minute. Yeah, I made a mistake. I'm going to leave it. I see a mistake that I made. I'm going to leave it for a moment. So I get positive 16. 1 plus 16 is 17. And I go 17 times negative 2 is negative 34. And then finally, negative 1 plus negative 34 is negative 35. Now, like I said, I made a mistake. I didn't mean to make a mistake, but it's actually quite helpful here. So first of all, what have I just done? Well, I will say all these numbers here, the very last one is my remainder. That's my remainder. So even if I didn't notice that I made a mistake so far, I would now notice I made a mistake, because I know the remainder should be 29. I got negative 35. So that means I've either made a mistake with this step right here, or I made a mistake with what I just did right now. And one good thing about these next couple lessons is quite often if we make a common silly little mistake, what I made was a common silly little arithmetic mistake, quite often we can catch it. Like our work kind of contradicts itself. So I now know there was a mistake because my remainder is negative 35. I knew it should be 29. So what was my mistake? Hopefully by now you've seen it. Right here. That right there, it should be positive 8 because it was negative 2 times negative 4. So positive 8. So it should become a positive. And then I go negative 2 times 8 is negative 16. And 1 plus negative 16 is negative 15. So I'll erase all these right here. And then multiply negative 15 times negative 2, which is positive 30. And then what do you know? Negative 1 plus positive 30 is 29. There we go. So I already said this last number is the remainder. So what's this? That's my quotient. What does it mean? Well, let's look at it like this. The negative 15 is my constant term. The positive 8 is my x term. The negative 4 is my x squared term. And I keep working my way up. The 1 is my x cubed term. And there's my quotient. Now notice, especially if I didn't make a mistake, and if I wasn't talking the whole time, I could have got to this quotient really, 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 really quickly. And the remainder right there. So write out my answer, that all of this here is equal to my quotient, x cubed minus 4x squared plus 8x minus 15. Okay, but there was a remainder, which is positive 29, so I have a bit more, plus 29 over x plus 2. And so using the sort of terminology we'll usually kind of use here, the parts I've highlighted in yellow is my polynomial. That's what we're dividing by. Into it, I'm dividing x plus 2. That's my divisor. And my remainder, in this case, was 29. And so again, that remainder of 29 doesn't mean too much to me, although it did allow me to kind of double check that I made or see that I made a mistake if I hadn't noticed it myself. But what I just did here is called synthetic division. It is a much, much faster way of doing the sort of long-winded process of long division with polynomials, as long as you're dividing by fairly simple binomials like x plus 2, x minus 2, x minus 17, all those would be fine. As soon as it's like 3x minus 17, then you're better off just doing this. Long division is a bit more time consuming, but it works on everything. All right, so like I keep saying, if this is your first introduction to this lesson, you definitely need practice. And you'll have some practice in class and then with homework. But I want to talk about my final problem, which is this. Determine a value of a so that this has a remainder of 0. Determine a value right there so this has a remainder of 0. When I go all the whole numerator divided by x minus 2. So how can I do this? Well, I will say, if you look at this and you feel like you need to do some division, I'm not saying that's impossible, but I don't need to. I don't need to do any division or synthetic division to figure out what a is. So how can I do this? Well, using the remainder theorem. Remember, if I'm dividing by x minus 2, I can figure out the remainder by replacing all these x's with positive 2. And if I replace all these x's with positive 2, I know I can find the remainder, except this time I know the remainder. The remainder is 0. So what can I do here? Let's go take my numerator, replace all the x's with positive 2, the opposite of what I'm dividing by. And so I have 2 times positive 2 cubed plus 2 to the power of 2 plus still a, I don't know what it is, times 2 plus 6. So notice what I've done is I took all my x's and replaced them with positive 2. Because I know, according to the remainder theorem, if I do that, whatever I get here will equal my remainder. But again, I know the remainder equals 0. So now notice, all I have left is one unknown variable, which I can solve really easily because everything here can just be simplified. 2 times 2 to the power of 3 is 2 times 8, or 16, plus 4, plus 2a, plus 6 equals 0. Suddenly, what maybe looked like a really complex question is turning into a very nice, pleasant equation. Combine like terms, I get 2a equals negative 26, a equals negative 13. And I was able to figure out that missing coefficient so without having to do any division. I have nothing against division, but using the remainder theorem, I could really quickly get there. Which leads me to the last sort of step. If this expression here in yellow, when you divide by x plus 2, has a remainder of 0, that tells us something. If the above quotient has a remainder of 0, that means x minus 2 must be something of that. Having a remainder of 0 is where remainders really matter. If you get a remainder of 0, it tells us something about what you're dividing, but I'm not going to tell you right now. So we will talk about this in class, but really, really important, and I'd rather not just say. Okay, so there's just a single word that goes in this blank. And if we can figure out what that word is, then we can start to see why the remainder does matter for certain scenarios. Why does a remainder of 0, what does that tell us? But I'm not going to tell you. So I'm going to stop there.